تمام. The two questions we'll be solving today were requested from Dr. Kamil for me to solve, and inshallah I'll try to solve them as best as I can. Uh, we'll start off with example 3.7 and we'll go on to example 3.8. Both of these examples can be found in slides and also in the book. First off, we'll take this example 7. Example 3.7 states a huge water reserve is drained with a two nominal schedule 40 galvanized steel pipe that is 60 meters long. The piping system is shown in figure 3.9. The fittings are regular and threaded. Determine the volume flow rate through the system if Z1 equals 5 meters and Z2 equals 2 meters. We'll start off the question by writing down all the givens that we have been provided with in the question. First was the fluid used through the piping system is water. The second being the dimensions of the pipe, which is two nominal schedule 40. The pipe length is 60 meters. The fittings are regular and threaded. Determine the flow rate through the system if Z1 and Z2 equals 2 meters. They also gave us the height at the inlet, which is 5 meters, and the height at the exit, which is Z2 equals 2 meters. The first thing we're going to do after we write down our given is we're going to utilize all this information to get as much as we can from the tables. First off, let us start by finding uh, the properties of water. Which if we go to the table, if we go to table B1 on page 10, you'll find that you can get the specific gravity, the absolute viscosity of the fluid which is used in any piping system that is standard. Now in this question, they told us that water is the fluid used. So we'll get the specific gravity and the absolute viscosity. Please make sure to use the right units when getting the absolute viscosity. In this question, the units have been given to us in meters. So we'll use the metrics, the English standard, which is Newton second per meter squared. Now, in the tables, they gave us the specific gravity and the absolute viscosity. Now, to change those, what we want out of them is the density and the viscosity, not the absolute viscosity. Now, to get the density out of specific gravity in English units is 1000 multiplied with specific gravity. Now, in the table, it tells us that water specific gravity is 1.0. So that means it's 1000 multiplied by 1.0, which equals 1000 kilograms per meter cubed. Now, viscosity is, by the way, this information can also be found on the bottom of the table, on the bottom of the page. All right, so if you're finding the values for different units, like slug per foot cubed, or in pound mass per foot cubed, you just need to go to the bottom of the page and you'll find the conversion units for them. Now, to find the viscosity of water, we just need to take this value and multiply it with 10 to the power of -3. So the absolute viscosity is 0.89. So it's going to be 0.89 times 10 to the power of -3 Newton second per meter squared. After that, let's go to find the diameter and the area of the pipe. Now they told us that it is 2 nominal schedule 40. We'll go over to the tables again, but this time we'll go to table D10, which can be found on page 22 of the booklet that Dr. Kamil gave you. And we'll go all the way down until we find 2 nominal schedule 40. Now, just for you to know, in the question, if they give you the nominal diameter, but they don't specify the schedule, then you always assume that it is standard. All right, only if they give you the nominal diameter and nothing else. But if they give you the nominal diameter and a specified schedule, then just get the values for the schedule that is provided. Now, in this table, we're able to find the inside diameter in centimeters and the flow area in centimeters squared. Now we can also find it in foot squared and foot, but in the question, it's easier to just use the same units. So D equals 5.252 centimeters. Now I highly suggest that when you're writing down the diameter and the area, I highly suggest that you convert them to meters. So 5.252 centimeters would be 0.5252 meters, and the area, as can be seen here, is 21.66 centimeters squared, which in meters would be 0.002166 meters squared. Now, the next given that we can find is the epsilon of the roughness of the pipe. Now, I forgot to write this down, but it is stated that in the question it is galvanized steel pipes. So we will go over to the tables again, and we will go to table 3.1 on page 28 of your booklet. We'll go all the way down to steel. We'll go to the galvanized section, and we'll get the values in centimeters. Right, you can also find it in foot, but again, we'll use centimeters. Now, in the table, in the roughness table, when you have a range like we do now, we won't take either one of them. What we will do is we will find the average between those two values. So epsilon for us would equal 0.006 plus 0.025 over 2, which would give us 0.0155 centimeter. Now in the question, they gave us regular and threaded, which would help us in finding the K value, but we will come to that later. So this is all the information that we were able to get with just reading the question. Now let's find out what the question actually wants us to do. In the last sentence, it tells us to determine the volume flow rate through the system. The volume flow rate is Q. So what we will do in thermal system design, the first half of the course, you will be using mainly the modified Bernoulli equation. You will use it in different ways, but it will come down to the same equation. You'll just be removing and adding onto the equation. The Bernoulli equation is written as so. All right. So this, just to clarify, is the pressure at the inlet, and this is the density of the fluid. This is the velocity at the inlet, the height at the inlet. This is the pressure at the exit, velocity at the exit, the height of the exit. All right. So in the question, they did not give us the pressure at either the inlet or the outlet, nor did they ask us to find it. So we will assume that P1 equals P2 equals atmospheric pressure. When we have this assumption, we could easily just cross out this and this from the modified Bernoulli equation. Also, they did not give us the velocity at the inlet or the velocity at the exit. So it would also be safe to assume that they equal each other, and we could cross out these two. Now, this part and this part, we cannot cross them out because they're connected to something else. So we'll keep them in the equation. Now, in the question, there wasn't any pumps or motors or anything of the sort involved, so we will also cross this out. And now we are just left with Z1 equals Z2 plus the friction factor times the length over the diameter multiplied with V2 squared over 2G plus the summation of K multiplied by V2 squared over 2G. Now this equation can be simplified a little by taking this and the velocity part of these two and using it as a common, giving us the equation as so. So this is the equation that we have. Now, Z1 and Z2 are given. The length is given. The diameter we were able to figure out. The only things that we don't have is the velocity, the friction factor, and the K value. Now, the K value, we are able to figure it out using the figure of that is given to us in the question. And they also told us that the fittings are regular and threaded. So we will go over to the tables again, and we will go to table 3.2. It would be on page 32. And here you can find the K values for all the kinds of possible combinations that you can have in a piping system. Now in the question, it does not state as much, all right? But in the exams, Dr. Kamil will specify exactly what this is and what this is. All right, now this is a basket strainer, and this is a globe valve. Now here, the piping system ends to the outside. There isn't anything containing it. So uh, we will also take the K value of the exit and the K value of the four elbows found here. So our K value, the summation of our K value will come down to the K value of the basket strainer plus four 90-degree elbows plus the K value for a globe valve plus the K value for the exit. So now if we go to the table, we'll see that the K value for the basket strainer is 1.3. And we can also see that the K value for a regular and threaded 90-degree elbow is 1.4. So we will multiply 4 by 1.4 since we have four 90-degree elbows, plus the K value for a globe valve, which is regular and threaded, which equals to 10, plus the K value for the exit, which is 1, which you could see here. Exit K value equals 1. Now adding all three to get the summation of K would be 17.9. Now the K value doesn't have a unit, so you just write 17.9. Now let's go back to our original equation. Now we have the value for K. The only two equations that we don't have is the friction factor and the velocity. So what we will do is we will rearrange the equation with respect to the velocity and the friction factor. But we will have the equation to be written as V as the unknown and F as the factor. So we will rearrange and play with the equation and we will plug in the values. The value for Z1 was 5 meters. Z2 was 2 meters. V squared. Now we could drop the use of V2 since now we only have one uh, type of velocity. 2 multiplied by 9.81 into the friction factor multiplied with 60 over the diameter. Now make sure that you use the diameter as meters, not as centimeters, since all our values are the value for the length is meters, the value for the gravity is meters per second squared, plus the summation of K, which is 17.9. Now we will rearrange this equation, as I said earlier, to find it, so as to help us find the velocity. So this is the equation that we end up with. We have two unknowns in this equation. We have the velocity and the friction factor. All right. Now, in order for us to find anything related to the friction factor, we need two other values. The value for Reynolds number and the value of epsilon over D. Epsilon referring to the roughness. So the equation for Reynolds number is V D over the nu, which could also be written as the density multiplied with the velocity, the diameter over the viscosity. Now we have the viscosity, we have the diameter, and we also have the pressure, the density. The only thing we don't have is V again, which is fine. We'll just write the equation with respect to V. So it will come down to 1000, which is the density, V, the diameter, which is 0.05252 over 0.00089, which is what we found here, which is the same as this. So now if we calculate it as it is, we'll come up with Reynolds number equals 5,000, no, 59,011.23 V, which is also 5.9 times 10 to the power of 4 V. Now epsilon over D is simple. We already have the roughness and we have the diameter. So we could simply write 0.0155 over 5.252. Now the roughness value in the table, we got it as in centimeters. And so we must also use the diameter in centimeters as well. This comes down to 2.95 times 10 to the power of negative 3, which is also 0.00295, but we'll round it up a little and we'll write it as 0.003. So now we have the Reynolds number, we have epsilon over D, and we also have the equation for V with respect to F. Now we will use all three equations in a trial and error process. Now, but before I continue, I just want to mention that in the slides and also the book, there's a mistake. When finding the Reynolds number, they use the wrong diameter. I don't know where they got this diameter from, but it's wrong. So just make sure that you use the same diameter that you calculated and the one that you found through the tables. So this will be equation 1. The Reynolds equation will be equation 2. Epsilon over D would be equation 3. So for our trial and error, we'll, before I carry on as well, let me just clarify that with Dr. Kamel, he doesn't really like force you to do many trials. Maximum that he will force you to do in a question or anything is 2, and that is the maximum that you'll do. Now, usually when we ask him later on, like in the semester, you will have questions which will take a long time in trial and error. And he would just tell us just do one iteration and that's it. Right. And but for the purpose of, education, we'll keep going until we find the right answer. But I was able to solve the question yesterday and I got it close enough for Dr. Kamel for Dr. Kamel to accept it. So we have 3 equations that we need to use for our trial and error. The first equation is for velocity. Our second equation is for Reynolds number, which was And our final equation is roughness over D, which we said we'll use as 0.03, 0.003. So in our first trial, we will assume the value for the friction factor to be equal to 0.01. And we will just plug in this value into this equation in order so that we can get a velocity. So we'll just plug in which is equal to 1.42 meters per second. And then since now we have the velocity, we can plug it into the second equation. And now we have a value for Reynolds number. We'll use these two values. We'll use this value for Reynolds number and this value for roughness over the diameter. And we will go over to the Moody diagram. Now the Moody diagram can be found in your table as well on page 29. Now there are different variations, but the one on page 29 is the one that you will use the most. Now, the Moody diagram is used as follow. You will need to get the Reynolds number and a value for epsilon over d. Now here it says millimeters, that the roughness should be in millimeters and the diameter should be in millimeters as well. But if you use the same units for both, you will get the same answer. So that's perfectly fine. Now we found roughness over D to be 0.03. So 0.03 can be found right here. The value for the Reynolds number is 8.4 times 10 to the power of 4. If you go down here, you'll see uh, down here you have 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, and so on. Now these tell you that now this value is 2 times 10 to the power of 3, 3 times 10 to the power of 3, and so on. And the same for the rest of this for the rest of this axis. So now since our value is 8.4 times 10 to the power of 4, we'll go here times 10 to the power of 4. We'll go to 8. And so this is 9. We'll go about halfway. We'll put the ruler halfway between, and we'll just draw a line straight up. And now we will follow this line for roughness over the diameter, this blue line, until we reach the point of intersection, which is right here. Once we reach this point, we will go directly to the left. This value is what this value is the friction factor. Now here we have 0.25, we have 0.25 and 0.03, and it goes in increments of 5, so it's 0.26, 0.27, and 0.028. Sorry, I forgot the 0. 0.026, 0.028, and 0.028. So this is approximately halfway between. So it would be safe to assume that it's 0.0275. So now we can go here and we see that the friction factor that we ended up with in our first trial is 0.0275, which is not equal to our first estimation of 0.01. So what we will do is we will do another trial and error, but this time we'll use the starting friction factor as 0.0275. And we will repeat the same process that we did in our first trial. We will write down the same equations. So V equals 3 over let me just double check my values. Yes, they're the same, which gives us 1.09 meters per second. We'll plug this value, this velocity value, into the Reynolds equation. And we'll do the same thing again. We will take we'll go back to the Moody diagram. We'll use the same roughness over diameter value, which is 0.003. But this time our Reynolds number came to be 6.4 times 10 to the power of 4. So we have 10 to the power of 4. We'll go to 6, and with 6.4, so we could assume it to be halfway between. We will line it up. We will go to the point of intersection, which is right here. We'll draw a line straight left, and we will get the new friction factor, which is 0.028. So our new friction factor, 0.028. Now it is close to our original value of friction factor, which is 0.0275. So if your value is around, if it's close to each other, then that's fine. You could just say close enough and move on. All right, you don't need, it's not necessary to get the exact same value. You just need your values to be close. So now since we have a proper friction factor, and now we have a proper Reynolds number, we have a proper velocity value, and no, we don't. We need to recalculate both our velocity values and our Reynolds number because now we have a new friction factor. Now the question originally asked us to find the value of the volume flow rate. The equation for the volume flow rate is the area multiplied with the velocity. We have found the area already from the nominal diameter and the schedule 40. And now we find the value for the velocity. So we can simply just plug the values in, which is the area is 0.002166 multiplied with 1.086, which gives us 2.352 times 10 to the power of negative 3 meters cubed per second. But you could also rewrite it as 2.36 liters per second. That is the answer for example 3.7. Now, does anyone have any questions? Tamam. Now we'll go on to the second question, example 3.8. This example can also be found in the slides and the book. And as I stated earlier, these two examples were suggested to me to solve by Dr. Kamel. Let's just jump straight into it. Example 3.8, figure 3.10 shows a piping system that consists of a line connected to two branches. When the bypass branch is closed off with its valve, the flow line is to deliver 0.3 foot cubed per second of benzene with a pressure drop of P1 minus P2 of 8.5 psi. Select a suitable size for the pipe if it is made of uncoated cast iron and has regular threaded fittings. The length of pipe required is 700 foot. Due to cost considerations, it is desirable to use Schedule 40 pipes. So the same as last question, we will write down the given, and we will try to extract all the values that we could get just from what we have. The first thing they gave us is the flow line is to deliver 0.3 foot cube per second. So they gave us the value for Q. They gave us the fluid used. They gave us the pressure drop, the maximum allowable pressure drop to be specific. They told us the material. They told us the connections of the pipes. They also gave us the maximum allowable length. And they also told us that they desire the pipes to be Schedule 40. Now they didn't give us a nominal diameter, so it is assumed that we must find the diameter ourselves. So let's start off this question the same way as last time. We have benzene. Out of that, we could find the density and the viscosity. If we go to the tables again, uh, benzene is right here. Specific gravity of 0.876, an absolute viscosity of 1.26 pound force second per foot cube. Now this question is not using metric units, it's using American units. So we'll be making sure to use these type of units from the tables. Now specific gravity is 0.876, and we want it in pound mass per foot cube. So we will write it as and for the absolute viscosity, we will do the same thing, 1.26 times 10 to the power of -5 pound force second over foot cube, squared. The next thing they told us is uncoated cast iron, which is cast iron is right here. With this foot, since it is uncoated, none of these apply. So the roughness is 0.00085. So now we would like to find the velocities value, any values that we can get. So we also know that an equation for the volume flow rate is A1 V1, which is also equal to A2 V2. So in this question, we could say that A1 is equal to A2 and that V1 is equal to V2. In the drawing and the figure of the question, they also gave us that Z1 equals 8 and Z2 equals 10 foot. So we will write those down as well. We can also find the K value for the question. Now here they specified in the question that we have a gate valve. This here is not a 90-degree elbow, but it is a T-joint. We have 1, 2, 3, 4, 5 90-degree elbows. So we can get the summation of K, which is the K value for a gate valve, plus the 5 multiplied with 90-degree elbows, plus 1 T-joint. Now, if you're wondering where I got these values, similar to how we did last question, we find them from table 3.2. The question specified that it is regular threaded fittings. So uh, we will use the 90-degree elbows regular 1.4 and the T-joint is right here, threaded. So it's 0.9 for all sizes. And the gate valve is right here, fully open. If it's not specified of how open it is, just use fully open. And I've never ran into a question where the gate valve is half open or half closed or whatever. Usually any valve is fully open. So now we have the value for the summation of K. But let us go back to this equation for a moment. So since we know that K equals AV, since A1 is equal to A2 and V1 is equal to V2, we could rewrite the equation for the velocity, Q over A. We know that the value for Q, we know what the value for Q is, and we know that the area, the surface area of a cylinder is pi d squared over 4. So 1 over A would just be 4 over pi d squared. So if you plug these two in, since A is in the denominator, you will get 4Q over pi d squared. Plug in the value, we can get 4 into 0.3, which is the value that the question gave us, pi d squared, which can finally be written as 0.382 over d squared. So now let's use the main equation that we used last question, which is the modified Bernoulli equation. But this time I'll just cut to the chase and write the equation as we need it to be. We have P1 minus P2, sorry. We have P1 GC over rho G minus P2 GC over 2G. Oh, sorry. This is the exact same equation I used last question, and this is the equation for the modified Bernoulli equation. I just cut to the chase and I rearranged it to how I would like it to be. Now, the value for the density is the same. The gravity is the same. The gravity as well is the same. So we could simplify this part of the equation with 22.4. 22.4, we got this value by taking this. So it's so plugging in these two with the gravities and such, we can get 22.4. We have the value for Z1, Z2, we have the length, the diameter, the K value. The only two things we don't have is the velocity and the friction factor. We know the value for gravity. Or we could write this equation differently by making it by just adding, subtracting, multiplying, and dividing to get it in a simpler form, which is if we rewrite the equation to get it with respect with to find f with respect to d, it would be written as so. And now we will try to find the Reynolds number. As I mentioned last example, if you have the friction factor, you need to find the friction factor by by having Reynolds number and the roughness over diameter ratio. Now, the Reynolds number can be found using this equation, specifying this is density, not pressure. So it will be now if you're wondering where we got this from, this is the value for D, which we equated here. We just plugged it into this equation. So now once we calculate as much as we can calculate, we can get Reynolds number to be since the squared will be cancelled by this D. And we have epsilon, sorry, the roughness over D. As you can see, our biggest problem in all three in this equation, which is equation 1, we will call it equation 1. This will be equation 2, and this will be equation 3. Our biggest problem is the diameter. So similar to last question, this previous question, we will do trial and error. Now last time, so I solved this question yesterday, and I was able to find it in 3 trials and errors. All right, and I will go through all 3 trials so that you get the idea of it. We will first assume a value for D, calculate the friction factor, and then go on to calculate the Reynolds number with the diameter that we assumed, and also the roughness over diameter ratio. So for our first trial, we will assume D to be equal to 1 over 4, which is equal to 0.25 foot. The friction factor, once we plug this diameter into the equation, is 0.0093. Now, this is the friction factor that we calculated. I just want to specify that matter. We calculated this friction factor. What we need to do right now is to calculate the Reynolds number and the roughness over diameter. Then we need to go on to the Moody diagram. And if the value of the friction factor from the diagram matches or is close enough to the friction factor that we calculated, then we can call it a day and move on. Now, the Reynolds number with this with this diameter would be 2.06 times 10 to the power of 5. The roughness over diameter ratio would be 0.0034. I'm specifying again that these two we were able to find from equations 2 and equations 3. The only thing we did is we plugged in the value for D. Now let's go to the Moody diagram. Now our roughness over diameter is 0.0034. So it is approximately 0.0034. It would be around here. We'll assume it to be here, so we'll just draw an imaginary line ourselves. Or you could just use 0.003. It is fine. Dr. Kamil, he will not be picky. All right, as long as your answer is close, he will count it as the right answer and he will calculate your answer as if that is the correct value, as long as you're close. So we have 0.003 and Reynolds number is 2.06 times 10 to the power of 5. So we have 10 to the power of 5, 2.06. So it's 2. Since it's 2.06, we'll just go here. We will draw a line straight up. We will go to the point of intersection, which is right here. and we will draw a line all the way left. Our value ends up being 0.027, let's say. So the new friction factor that we got from the table is 0.027. So this friction factor does not equal this friction factor, so we will have to try again. But this time, similar as last time, for trial 2, we will start with a higher d, with a higher diameter. So we'll start with 1 over 3. So, so for our second trial, we decided to use 1 over 3, which is equal to 0.333 foot. After plugging this diameter into the friction factor equation, we got this to be our friction factor. We recalculated the Reynolds number and the roughness over diameter ratio, which is these are the two values that we found. And we will do the exact same thing over again. So we have 1.55 times 10 to the power of 5. Our epsilon was, our ratio was 0.00255, which is between these two values. So we will place our ruler around here and we will draw a line all the way left. Our value came out to be 0.02, let's say 0.026. Now 0.026 is not the same as 0.484, but compared to our first trial, it's a lot closer. All right, so we will try one more time. This time we'll use a diameter between 1 over 4 and 1 over 3. So we will go with a diameter of 0.3 foot. Now when plugging in this diameter, into the first equation, we get 0.027. Now this diameter plugged into the Reynolds number gives us 1.72 and a ratio of 0.0028. So let's go 0.0028. It is also between these two. So we'll say it's like around here. And 1.72 times 10 to the power of 5. So it's like around here. No, I'm sorry, it's like around here. And we agreed if there's a value between these two, you just draw an imaginary line in your head or whatever you're comfortable with, whether you want to trace it, which is, in my opinion, a waste of time. Just as I said earlier, you don't have to be exactly correct. So let's say it's around here. We got a value of 0.027, which is also the exact same value as the friction factor which we calculated. So now since we have two friction factors which is the same, we could confidently say that the diameter is 0.3 foot. But the problem with that is we can't really say uh, which diameter we would like to use. We need to go to the tables and we have to choose diameter from there. Now, the diameter that we calculated to work in our system is 0.3 foot, correct? So we will try to go to the table D1, and we'll look at the the foot, until we find a diameter close to 0.3. All right, the closest to is 3.5, 3, 1/2 nominal diameter, and 4. These two right here. Since this one and this one are close, all right, what we will do now, usually in a piping system, you would uh, you would always prefer to go with the diameter that is larger. So when you have two options, it is best to go with the larger one. So we will go with 4 nominal diameter. Now, in 4 nominal diameter, schedule 40, because that was the that was specified in the question. We have a diameter of 0.3355 foot. So now we will calculate the velocity. Sorry, I forgot to get the area, which is 0.08841. We have the volume flow rate, and now we have the area. Which gives us a velocity of approximately 3.39 foot per second. So what we will do with this information is we will get the Reynolds number. We will plug this velocity into the original equation to get the Reynolds number, which is 1.53. We will get epsilon over diameter, which is 0.00253. And we'll also get the friction factor, but the friction factor we will get from as well the Moody diagram. And then we'll plug all of this information, all these values into our original value, into our original equation, the modified Bernoulli equation. But this time we are checking for the pressure. So we will write the equation as so. What we're trying to find is P1 minus P2, because in the question, they told us it cannot exceed 8.5. So when calculating everything and using their calculators, you get a pressure difference of 5.1 psi, which is less than 8.5 as the question wanted us to do. It wanted us to find the pressure difference lower than an 8.5. Now, yesterday when I was solving this example, I tried to solve it uh, for uh, 3.5 nominal diameter schedule 40. As you remember, those were our two options: 4 nominal diameter and 3.5 nominal diameter. And after doing all of this, I won't write it down. I found a pressure difference of 8.9 psi, which is above the required 8.5. So this is the correct answer. Always use a higher diameter unless it's special occasions, unless like special occasions or special scenarios, which we will go over um, after your midterm. You will take it, but for now we'll just go uh, just choose the bigger uh, option. If you have more than one option, always choose the bigger option. All right, so those were the two examples that Dr. Kamil told me to solve and to explain. Do you have any questions about either one of them? Okay, so I'm done for our tutorial today. It was an hour and a half, which is good. We solved two examples. But before I leave, I would just like to give you 3 tips in this course. The first, and this goes a long way, pay attention in the lectures. Dr. Kamil's the way he explains is perfect. All right, when I was taking it with him, I didn't go over the slides for the midterm or the final. I just went straight to the examples because I was able to pay attention in the lectures. And also in the lectures, he will go over some mistakes that are in the slides and the book. So if you don't pay attention, you might miss those small details. And it will also give you like small things that you could do to like help you solve questions. All right. So I highly advise you to really pay attention to Dr. Kamil's lectures. The second I could give you is in this course, you will have two projects and about five, maybe six quizzes, right? You probably already did one quiz, which was in person, but the rest of your quizzes will be online. All right, these quizzes won't be online live. He will give you like a project, not a project, a question to solve, and he'll give you maybe a week, possibly 2 weeks to solve it. All right. Now, these questions, I highly, highly suggest that you work on them. I'm not saying do all the work, but once your other group mates are done doing their part, since these quizzes are going to be the quizzes and the projects, since the quizzes and the projects are group based, uh, don't just hand all the work off to someone else. Try to do a part or all of it if you want, but make sure that you understand the parts that your group mates did. The third, and this is honestly the most important uh, tip that I could give you, use a physical copy of the tables. I don't care if you have iPads or laptops or you're using your phones. In the midterm and in the final, you will only be allowed physical copies of the tables. All right. And the tables are 69 pages. All right. And that is excluding the other stuff which I uploaded. This is something else that you will take later on, but this is 15 pages as well, plus the 5 pages of Omar Zaidan's step-by-step design problem. All right. When you have, and a few other pages that I will give to you when the time is right. Um, when you have all of this, it will get messy, it will get hectic. But if you study using a physical copy of all of this, you won't have a problem in the midterm and the final. When I took it last semester, so many people had the same problem of them not being able to navigate the tables. All right. So if you want, print it out in any way that you are comfortable with and put little like tabs on the top or on the sides to help you go from one end to the other end of the tables. Other than those three, I guess that you should be all good. Inshallah, that this tutorial was helpful. Next tutorial, inshallah, I will try to maybe solve a previous of the midterm. I'm not sure. This is all that I have.